Limitations of floats. Like int and uint8, Swift floating point types are represented in a fixed amount of space. A double occupies 64 bits. As a result, some floating point numbers can't be represented exactly. They can only be approximated. Below is the implementation of the change for purchase price function. You can see that both its parameters are doubles, enabling the function to handle prices as they're typically expressed, in dollars and cents with a decimal point. It's not important to study this code in detail. You'll be using it in some exercises. So looking at this, we have a function for change, and for the amount given, we have a double. Purchase price is a double and returns an array of denomination type. So handle illegal values. So if purchase price is greater than 500 or purchase price is less than 1 penny, print purchase price must be between 1 cent and $500. And it returns the empty array. If amount given is less than purchase price, print insufficient amount and then the amount given to purchase item at price, what the purchase price is, and returns also an empty array. Convert amount to pennies. So let amount in pennies get integer amount given times 100. Let purchase in pennies get integer purchase price times 100. Calculate change in pennies. So change in pennies gets amount in pennies minus purchase in pennies. So we're calculating everything in pennies, and this is just making them into integers. Set up an array of all available denominations. So variable denomination, and then this is the denomination type of an array. And then we have a 10, 5, 1, quarter, dime, nickel, penny. So those are all of our possible things that we can give change for, or change with. Initialize the change to an empty array and the current denomination to the largest. So variable change, denomination, type. So this is just initializing to that type. Variable current denomination gets denominations at that first item. So it's going to be 10. Add denominations to the change. So while change in pennies is greater than 0, if the current denomination is too large, choose the next smallest one and skip to the next iteration of the loop. So if current denomination value in pennies is greater than change in pennies, denomination remove at 0. And the current denomination is denominations at that first item in the array, and continue. All right, again, you don't need to know everything about what this does. It's just giving you all of the code. Abstraction will make you be able to use this and not know exactly how every tiny piece of this works. So if you're a little bit lost, that's okay right now. Some of this stuff you haven't seen yet. So add one of the denomination to the change and subtract the amount from the change due. So change in pennies minus equals current denomination value in pennies, and then change append current denomination. So this is appending the denomination to your change, essentially. And then return change. So once it makes the entire array of the change that you should get, that's what it's going to return. So this example doesn't work. Change for a 10, purchase price $8.95. It should be a 1 and a nickel, and it's a 1, a nickel, and a penny. So we saw that at the end of the last lesson. Lines 20 and 21 of change for purchase price, 20 and 21 are here. Replicated below, convert the two argument values to whole numbers of pennies, represented by integers. So this just makes, instead of using a double, it will make it into an int by multiplying it by 100. So $1 would be 100 pennies. So the int initializer truncates the input floating point number by removing all digits past the decimal. So if it was $1 was worth 1.001, it would get rid of that extra 1 at the end. So the result of the function uses these values to calculate change. The function itself has no logical errors. It should work for all valid inputs. The problem is that doubles don't always work the way you expect them to. If you scroll up to those lines in the function, you might spot the error in the results sidebar. Take a look in the results sidebar for the line below to see it more clearly. So 895 is 894,999,999 repeated. Some strange behavior is going on. Due to the limitations of the double type, the double's literal 895 isn't actually that value when it's represented in the computer. So when you multiply it by 100, the result isn't 895.0, but 894.999 repeated. Doubles have other limitations as well, such as those that only crop up in addition operations. These can even fool you by appearing correct in the results sidebar. So we have let A get the double 0.05, let B get the double 0.01, correct in the results sidebar. A plus B, oh, interesting. And then A plus B is equal to 0.06. That is false because this is actually what it's equal to according to the computer's math. So print A, print B, print A plus B. That's a little wonky. Certain values of double just can't be represented accurately. This limitation can have an impact on everyday code, depending on how it uses numbers. In the case above, a quick solution is to multiply the value by 100, then round to the nearest cent before converting it to an int. So if we let price get 8.95, let price in pennies get price times 100, so this would convert it to an int, so it would be 895, so that would be in pennies. Rounded price in pennies gets price in pennies rounded, so produces a new double. Let integer price in pennies get int rounded price in pennies. So this is saying this is the rounded version of this after multiplying it by 100. So that is actually going to give us that correct 895.